Tonight, we're going to sit together inside one of the most unsettling silences in the history of human thought. Not the silence of a quiet room, or the silence of a sleeping house. Something far older, far deeper. The silence of a universe that is 13.8 billion years old, that contains more stars than every grain of sand on every beach on Earth combined, and that has, as far as we can tell, never once sent us a message, never whispered back, never answered. You are lying here tonight beneath an ocean of 2 trillion galaxies, each one holding hundreds of billions of suns, and across all of that, across distances so enormous they dissolve all meaning, there is nothing, complete silence. And that silence, when you really let yourself feel it, is one of the most terrifying things our species has ever had to sit with. Here is what makes it so strange. The numbers say we should not be alone. The mathematics of star formation, of planetary chemistry, of the 4 billion years it took life to climb from a single cell to a creature capable of wondering about its own existence, all of it points toward a universe teeming with minds. Scientists ran the calculations, they built the equations, they pointed their telescopes at the sky and began to listen. And what they found, after more than 60 years of searching every frequency, every direction, every method available to us, was a silence so absolute it begins to feel like an answer in itself. By the end of tonight, you're going to understand exactly why that silence may be the most important and most disturbing discovery our civilization has ever made, even though almost no one is talking about it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. There is a possibility that has kept physicists and philosophers awake for decades, a possibility so cold and so vast that most people, when they first encounter it, instinctively look away. It is the possibility that we are not merely rare, that we are not simply difficult to reach across impossible distances, but that we might be, in some profound and final sense, the only ones who ever looked up, the only ones who ever asked. A single candle in a darkness so complete that the candle itself can barely comprehend the size of the room it is standing in. Tonight, we're going to walk into that darkness together, slowly, carefully, and without looking away. Now, let's begin. There is a question that has no comfortable answer. It has been sitting at the edge of human thought for decades, growing quietly in the dark, and most people never look at it directly, not because they cannot find it, but because once you really see it, once you hold it in your mind and feel its full weight, it changes something. It shifts the way the night sky looks. It changes what you hear when you step outside and stand under the stars in the quiet. The question is simple, terrifyingly simple. In a universe this old, this vast, this full of worlds, why has no one ever spoken to us? Tonight, I want to take you somewhere most science documentaries are afraid to go. Not into the physics of black holes or the chemistry of distant planets, though we will pass through all of that along the way. I want to take you into the silence itself, the silence that sits between every star you have ever looked at, the silence that has been the only answer to every signal we have ever sent. 60 years of listening, millions of frequencies scanned, entire careers devoted to a single question. And the universe, in return, has offered nothing but the soft hiss of background radiation left over from the beginning of time. That hiss is not a message, it is the sound of emptiness. I want you to imagine something with me. Picture the most remote place you have ever been, a mountain trail at 2 a.m. maybe, or an empty road in the middle of a desert with no lights in any direction. Think about how quiet that felt, how the darkness seemed to press close, how the absence of the other people made you aware in some deep animal way of just how alone you were in that moment. Now I want you to multiply that feeling by a number so large it has no name in ordinary language, because that is what we are actually dealing with tonight. Not the loneliness of a quiet trail, the loneliness of a species on a small rock circling an ordinary star in a galaxy of 400 billion stars, in a universe of 2 trillion galaxies, and finding, no matter how hard or how long we listen, nothing listening back. Here is the thing most people do not realize about that silence. It is not what scientists expected. When researchers first began thinking seriously about whether other civilizations might exist, they were not pessimistic. They were not cautious. They were, if anything, almost certain that the universe was full of life. The mathematics pointed that way. The sheer scale of creation pointed that way. In 1960, a young astronomer named Frank Drake sat down and built an equation, a simple framework to estimate how many communicating civilizations might exist in our galaxy alone. When he ran the numbers, the answer was not 0. It was not even close to 0. It suggested that our galaxy, just our galaxy, should be home to dozens, perhaps thousands, perhaps tens of thousands of civilizations advanced enough to communicate across space. The universe, by all rational expectation, should have been loud. And yet, the silence. That single word carries more weight than almost anything else in the whole of modern science. And yet, the silence. It has a name now. Scientists call it the Fermi paradox, after the physicist Enrico Fermi, who first asked the question aloud over lunch in 1950, in a way so plainly devastating that no one at the table had a good answer. He simply said, "If intelligent life is so likely, where is everybody? Where are the signals, the ships, the megastructures, the one unmistakable sign that someone else, somewhere out there, made it as far as we have?" The question was casual. The implications were not. Over the course of tonight, we are going to explore every serious answer that scientists and philosophers have offered to that question. Some of them are strange, some of them are almost comforting in their way, and some of them are so unsettling that I want to approach them slowly, carefully, the way you approach something in the dark that you're not entirely sure you want to see clearly. Because buried inside the Fermi paradox is not just a puzzle about alien life. There is something about us in there. Something about what it means to be the kind of creature that looks up and wonders and hears nothing back and keeps wondering anyway. Before we go any further, I want to say something about how we are going to travel through this together tonight. I am not going to rush. This is not a race through facts and figures. The cosmos does not reward rushing. What I want is for you to feel each piece of this as we go, to let the scale settle into you slowly, the way cold settles into a room when a window is left open. Some of what we discuss will be genuinely difficult to sit with. That is not an accident. I think the difficulty is the point. The most important things we have ever understood about our place in the universe have always required us to be willing to feel small, to sit inside an uncomfortable truth without immediately flinching away from it. What I can promise you is this. By the time we reach the end of tonight, the silence will not feel the same way it does right now. It will be deeper, yes, more precise. You will understand exactly what it is made of, and how long we have been listening into it, and what the most honest minds on Earth think it might mean. But there is something else that waits on the other side of all this darkness. Something that I find, in a quiet and unexpected way, genuinely moving. Something about the fact that we are here at all, asking these questions, lying awake under this enormous and indifferent sky and refusing, stubbornly, beautifully, to stop caring about the answer. We will get there. But first we have to go into the silence. We have to understand what we are actually dealing with. We have to let ourselves feel, fully and without looking away, just how alone we might really be. The journey starts here, in the dark, with a question no one has answered. And tonight, that question is ours. I want to start with a number. Just one number, and I want you to sit with it for a moment before we move on. The observable universe, the portion of the cosmos that light has had time to reach us from since the beginning of everything, is approximately 93 billion light-years across, not miles, light-years. A single light-year is the distance light travels in one full year, moving at just under 300,000 kilometers every second. In 1 year, light covers about 9.5 trillion kilometers. Now multiply that by 93 billion. The number you arrive at is so large that it functionally dissolves into abstraction. It stops feeling like a measurement and starts feeling like a myth. But it is not a myth. It is the actual size of the room we are sitting in. Let me try to bring that down to something your mind can hold. If you were to shrink the entire observable universe down to the size of Earth, our own Milky Way galaxy would be smaller than a single atom. Not a small atom. An atom. The whole sweep of our galaxy, 400 billion stars arranged in a spiral 100,000 light-years wide, reduced to something too small to see, too small to touch, too small to measure with any instrument we currently possess, and the Milky Way is not a small galaxy. It is, by most standards, a large one. There are dwarf galaxies that orbit our own like small moons orbit a planet. We are not a minor feature of the cosmos. We are simply lost inside something that has no meaningful edge. Within the observable universe, astronomers estimate there are approximately 2 trillion galaxies. That number was revised upward dramatically in 2016, when researchers reanalyzed data from the Hubble Space Telescope and realized that previous counts had missed the vast majority of smaller, fainter galaxies lurking in the deep background. 2 trillion. Each one of those galaxies contains, on average, hundreds of billions of stars. Some of the largest galaxies we have found contain more than 100 trillion stars on their own. The total number of stars in the observable universe is estimated to be around 2 times 10 to the power of 23. That is a 2 followed by 23 zeros. It is approximately 10 times more stars than there are grains of sand on every beach and every desert on the entire surface of Earth. Here is why that number matters for our story tonight. For most of human history, people looked up at the night sky and saw lights, fixed, cold, beautiful, but inert. Points of fire set into a dome. It was only in the last few centuries that we came to understand that each of those lights is itself a sun. An entire star, often larger and hotter and more powerful than our own, existing at a distance so extreme that all its fury is compressed into a single quiet point of light. And it was only in the last few decades that we confirmed what astronomers had long suspected, that most of those stars have planets. Not some of them, most of them. Current estimates suggest that our galaxy alone contains more than 1 trillion planets, 1 trillion worlds, just in our neighbourhood of the cosmos. Of those trillion planets, a significant fraction orbit within what astronomers call the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planetary surface. Water, as far as we know, is the essential ingredient. Every form of life we have ever discovered, every organism in every environment on Earth, from the deepest ocean trench to the frozen interior of Antarctic ice, requires liquid water to function, and the galaxy appears to be full of places where water could exist. The planet Kepler 452b, discovered in 2015, orbits a star very similar to our Sun, at a distance very similar to our own, in a system that is 1.5 billion years older than Earth. If life works the way we think it does, that world has had more time to develop it than we have. So the scale is extraordinary. The conditions appear to be widespread. The chemistry of life, carbon, hydrogen, nitrogen, oxygen, the building blocks of every living thing on this planet, those elements are not rare. They are among the most common in the universe. Amino acids, the molecular components of proteins, have been found inside meteorites. They form spontaneously in the cold gas clouds drifting between stars. The universe appears to be a place that is, at a chemical level, trying to make life. The ingredients are everywhere. The potential locations are numbered in the trillions. And yet, here is what keeps pulling us back to that disturbing silence. Across all of it, across all 2 trillion galaxies and all those billions of trillions of stars and all those countless worlds, we have not confirmed a single other instance of life. Not a microbe, not a signal, not a structure, nothing. I want you to feel that contradiction fully because it is the engine of everything we're going to explore tonight. On one side, a universe of almost incomprehensible size and abundance, built from the same chemistry that built us, scattered with worlds that orbit in the warmth of their stars, billions of years old, billions of years in which something could have started, something could have grown, something could have looked up just as we are looking up right now. On the other side, silence. Perfect, unbroken, decades-long silence. The two things should not be able to coexist. The math says the universe should be crowded. The evidence says it is empty. That gap between what should be and what appears to be is one of the deepest unsolved problems in all of science. And there is one more layer to this that I want to add before we move forward, because it makes the silence even stranger. The universe is not just large, it is old. 13.8 billion years old. Life on Earth took about 4 billion years to go from simple chemistry to a civilization capable of building radio telescopes. That means that if the same process happened elsewhere, even just a little earlier, those civilizations have had billions of years more than we have. Billions of years to develop technology, to spread, to build things that could be seen from across a galaxy. The universe has had more than enough time for intelligent life to fill it completely, many times over. The silence in that context is not just surprising, it is almost impossible to explain. And that impossibility is where our story truly begins. In the autumn of 1961, a group of 10 scientists gathered at the National Radio Astronomy Observatory in Green Bank, West Virginia. They were not there to observe the sky, not exactly. They were there to do something that had never been done before in the history of science. They were there to sit down together and try to calculate how many other civilizations might exist in our galaxy right now, at this moment, capable of communicating with us across the void. The meeting was small, the room was quiet, but what came out of that gathering was an equation that would go on to haunt astronomy for the next 6 decades and counting. It was called the Drake equation, named after the young astronomer Frank Drake, who wrote it on a chalkboard that morning, and what it said, when you followed it all the way through, was deeply and profoundly unsettling. The equation itself is not complicated. That is part of what makes it so powerful and so disturbing. It does not require advanced mathematics. It requires only that you multiply a series of factors together, each one representing a piece of the puzzle of how a communicating civilization comes to exist. You start with the rate at which new stars form in our galaxy each year, then you multiply by the fraction of those stars that have planets, then by the number of those planets that could potentially support life, then by the fraction where life actually emerges, then by the fraction where that life becomes intelligent, then by the fraction of intelligent civilizations that develop technology capable of sending detectable signals into space, and finally you multiply by the average length of time such a civilization continues to transmit. Multiply all those factors together and you get a number representing how many civilizations should be out there right now, in our galaxy alone, trying to make contact. When Drake and his colleagues ran those numbers in 1961, using the best estimates they had available at the time, the answer they arrived at was somewhere between 1,000 and 100 million civilizations. 1,000 at the conservative end, 100 million at the optimistic end. Even the most cautious figure in the room suggested that our galaxy should be alive with intelligence. The scientists who gathered at Green Bank were not dreamers or science fiction enthusiasts. They were rigorous, skeptical professionals, and the math kept telling them the same thing. The universe should be crowded, the silence should not exist. Now, more than 60 years later, we know some of those factors far more precisely than Drake and his colleagues did, and in some ways, the updated numbers make the paradox even sharper. Take the first factor, the rate of star formation in the Milky Way. We now know that our galaxy produces approximately 1 to 3 new stars per year, and has been doing so for billions of years, giving rise to a total of somewhere around 400 billion stars currently burning in our galaxy. Take the second factor, the fraction of stars with planets. When Drake wrote his equation, no one had ever confirmed the existence of a planet orbiting another star. Today we have confirmed more than 5,500 exoplanets, and statistical modelling suggests that virtually every star in the galaxy has at least one. The first 2 factors of the equation, the ones we can now measure directly, are far more encouraging for the existence of life than anyone imagined in 1961. The third factor is where things begin to get uncertain, and where the equation starts to reveal its hidden weight. How many of those planets actually sit in the habitable zone of their star? How many have the right conditions for liquid water, the right atmospheric chemistry, the right geological activity to maintain a stable surface over billions of years? Here the estimates vary. But even cautious astronomers now believe that tens of billions of planets in the Milky Way alone sit within their star's habitable zone. Tens of billions of potentially life-friendly worlds in a single galaxy out of 2 trillion galaxies in the observable universe. The scale of the opportunity, when you let yourself feel it, is almost impossible to absorb. But then comes the factor that fractures everything, the fraction of habitable planets where life actually begins. This is the number we do not know. This is the number where scientific opinion splits into 2 camps, so far apart they are barely having the same conversation. One camp, often called the optimists, points to the fact that life appeared on Earth extraordinarily quickly. Within a few 100 million years of the planet cooling enough to support it, microbial life was already present. To the optimists, this suggests that life is not a miraculous accident, but a near inevitable consequence of the right chemistry meeting the right conditions. If it happened here that fast, it probably happens everywhere conditions allow. The other camp looks at the same data and sees something different. They point out that we have exactly one example of life arising, one data point, and drawing universal conclusions from a single data point is one of the most dangerous things a scientist can do. Perhaps life on Earth arose through an extraordinary sequence of chemical accidents, so unlikely that, even given billions of years and trillions of planets, it has only happened once. Perhaps the origin of life is not a gentle slope but a vertical cliff, a step so improbable that the universe, despite all its abundance, has only managed to climb it in one place. We genuinely do not know which of these views is correct. And that uncertainty, sitting at the heart of the Drake equation, is where the silence begins to feel less like a puzzle and more like a warning. And then there is the final factor, the one that Drake himself described as potentially the most important and the most frightening of all. The average length of time a technological civilization remains detectable. How long does an intelligent species survive after it develops the ability to communicate across space? How long before it destroys itself, or falls silent for reasons we cannot yet imagine? If the average lifespan of a communicating civilization is only a few hundred years, then even if intelligence arises frequently, the chances of two civilizations overlapping in time and space, close enough and long enough to find each other, becomes vanishingly small. The galaxy could be full of ruins, full of civilizations that burned brightly and then went quiet before anyone could hear them. The silence in that case would not mean we are alone, it would mean we are late, or early, or simply unlucky in our timing. What Frank Drake built in that quiet room in West Virginia in 1961 was not just an equation, it was a mirror that reflects back the full strangeness of our situation, the fact that we are a species intelligent enough to calculate the probability of our own cosmic companionship, but not yet wise enough to know whether that companionship exists. Every factor in the equation is a door, and behind some of those doors the view is deeply, quietly terrifying. Tonight, we are going to open them, one by one, and look at what is on the other side. It was the 15th of August, 1977. A volunteer astronomer named Jerry Ehman was sitting at a desk, doing something that sounds almost unbearably tedious, but was in fact one of the most important jobs in science at the time. He was reviewing a paper printout of radio data collected by the Big Ear Telescope at Ohio State University, a telescope that had been scanning the sky for unusual signals as part of an early SETI program. The data came out as columns of numbers and letters, each character representing the intensity of a radio signal received from a particular patch of sky. Most of the printout was unremarkable. Ordinary background noise, the quiet static of an indifferent universe. And then Ehman turned to one particular column and everything changed. The sequence he saw was 6, E, Q, U, J, 5. In the coding system the telescope used, numbers and letters represented signal intensities on a scale from 1 to 36, with numbers covering 1 through 9 and letters covering 10 through 35. A signal of intensity 6 was moderately strong. A signal coded as E was stronger still. But the peak of what Ehman was looking at, the letter U, represented an intensity of 30, on a scale where background noise typically registered as 1s and 2s. It was not just a strong signal, it was an extraordinary signal, a signal that rose and fell in almost exactly the pattern you would expect from a transmission, originating from a fixed point in deep space, as the rotating Earth carried the telescope's beam across it. Jerry Ehman picked up his red pen, and in the margin of the printout next to that sequence, he wrote a single word. Wow! That handwritten exclamation, scrawled in red ink on a piece of computer paper nearly 50 years ago, became one of the most famous annotations in the history of science. The signal it marked has been known ever since as the WOW signal, and it remains, to this day, the strongest candidate for an extraterrestrial radio transmission ever detected. It arrived on a frequency of 1,420 MHz, which is significant in a way that still raises the hairs on the back of the neck when you understand it. That frequency corresponds to the natural emission of hydrogen, the most abundant element in the universe. For decades, astronomers had theorized that if any civilization wanted to send a signal that another civilization might think to look for, they would choose the hydrogen frequency. It is the one channel that any technologically capable species would know to monitor. It is, in a sense, the universal calling frequency. And something, on the night of the 15th of August 1977, was broadcasting on exactly that channel. The signal lasted for exactly 72 seconds. That was not a limitation of the transmission itself. That was the length of time the telescope's beam could track any single point in the sky before Earth's rotation carried it onward. What happened after those 72 seconds, whether the signal continued or stopped, whether it pulsed or was continuous, whether it carried encoded information within it, all of that is unknown. The Big Ear telescope was not designed to immediately re-examine a point of interest. It simply moved on, collecting data, and by the time anyone realized what had been recorded, the moment had passed. In the days and weeks that followed, astronomers pointed every available instrument at the region of sky where the signal had originated, a patch of space in the direction of the constellation Sagittarius. They listened, they scanned, they waited. The signal did not repeat. In the decade since 1977, the WOW signal has been the subject of intense scrutiny and genuine scientific debate. Researchers have proposed numerous terrestrial explanations: radio frequency interference from human technology, a reflection of Earth's own radio emissions bouncing off a piece of space debris, a natural astrophysical phenomenon not yet catalogued in 1977. Each of these explanations has been examined carefully, and each has problems. The signal's behaviour, the way it rose and fell in intensity precisely as expected, for a source fixed in deep space, rather than moving with Earth's surface, is very difficult to explain with terrestrial interference. The hydrogen frequency, while not legally protected from all uses, is closely monitored and was not known to be in use by any satellite or military system at the time. The natural astrophysical explanation remains possible but unconfirmed. We have never found a known natural source capable of producing a signal with those precise characteristics. In 2016, an astronomer named Antonio Paris proposed that the signal could have been caused by a hydrogen cloud surrounding a pair of comets that were in that region of sky in August of 1977. The hypothesis was testable. When those same comets passed through the same frequency range again in 2017, Paris's team observed them and detected no signal remotely resembling the WOW signal. The comet hypothesis, while creative, did not hold up to scrutiny. The scientific community remains divided. The honest answer, the one that most astronomers will give you if you press them, is that we do not know what caused the WOW signal. And not knowing is, in its own quiet way, one of the most unsettling positions science can find itself in. What I find most haunting about the WOW signal is not what it might have been, it is what happened after. The response of the scientific community, the most sophisticated civilization on this planet to potentially the most important 60 seconds of radio reception in human history, was to listen harder, to point more telescopes at that patch of sky, to devote years of careful, patient attention to an area of the cosmos roughly the size of the full moon as seen from Earth. And in all the years of listening that followed, across every frequency, with equipment far more sensitive than anything available in 1977, the silence returned and did not lift. The signal came once. It fit the profile of what we were looking for almost perfectly, and then it was gone, as if whatever had sent it had no interest in repeating itself, or had never been there at all. There are nights when I think about Jerry Eamon sitting at that desk, turning through pages of static, and I feel something that is hard to name. He was an ordinary person doing ordinary work, and for 72 seconds the universe handed him something that might have been the most extraordinary moment in the history of our species, a whisper from across the void, a sign that the silence had briefly cracked open. And then it closed again. The pen mark he left on that paper is still there, in the archives at Ohio State University. 6EQUJ5. Wow! The signal never came back, and the sky, patient and enormous and utterly unmoved, went on saying nothing. I want you to imagine a job. Not a glamorous job, not a job that gets written about in newspapers or celebrated at dinner parties, but one of the most quietly extraordinary jobs a human being can hold. You arrive at work, you sit down at your instruments, and you listen. You listen to the sky. You listen across dozens of frequencies simultaneously, scanning millions of channels for a pattern, a pulse, a sequence that does not belong to the natural hiss and crackle of the cosmos. You do this for years, then for decades. You refine your equipment, you expand your search, you recruit colleagues, you build better instruments, you listen harder. And the sky, across all those years and all those frequencies and all that patient, dedicated attention, says nothing back. This is not a hypothetical scenario. This is the actual working life of the scientists who have dedicated themselves to the search for extraterrestrial intelligence. And the silence they have accumulated is one of the most scientifically significant silences in history. The story begins in April of 1960, 2 years before Frank Drake would write his famous equation on a greenbank chalkboard. Drake was 29 years old, and he had convinced his institution to let him do something that most of his colleagues considered, at best, eccentric, and at worst, a waste of valuable telescope time. He pointed the 85-foot radio telescope at Greenbank toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, both within 12 light-years of Earth. He chose a frequency near the hydrogen line, for the same reasons that would later make the WOW signal so striking, and he listened, for approximately 200 hours over several weeks, for any signal that deviated from natural background noise. The project was called Ozma, named after the Queen of the fictional land of Oz, a place very far away and very difficult to reach. He heard nothing. But he had started something that would not stop. What followed Ozma was not a single organised program, but a gradual, decentralised accumulation of efforts, spread across institutions and countries and decades, each one pushing the search a little further, covering a little more sky, scanning a little more of the electromagnetic spectrum. By the 1970s, Soviet astronomers had conducted their own searches, using different methods and different assumptions about what a signal might look like. In the 1980s, NASA began funding a systematic SETI program that would eventually grow into the most comprehensive search ever attempted. In 1992, on the 500th anniversary of Columbus's arrival in the Americas, NASA officially launched the High-Resolution Microwave Survey, a project designed to scan tens of millions of frequencies across the entire sky. It was the most ambitious listening project in human history. Congress cancelled its funding 1 year later, citing budgetary concerns. The silence, it seemed, was also expensive to hear. The search did not die with the NASA funding cut. The SETI Institute, a private research organisation founded in 1984, carried the work forward with private donations and foundation grants. In 1999, a project called SETI at Home was launched, allowing millions of ordinary people around the world to donate the idle processing power of their personal computers to help analyse radio telescope data. At its peak, SETI at Home was one of the largest distributed computing projects ever run, with more than 5 million participants in more than 200 countries. Those millions of computers processed an enormous volume of data. They found interesting candidates, signals that warranted closer examination. Every single one, upon further analysis, turned out to have a terrestrial explanation. Radio frequency interference, satellite transmissions, reflections of human-made signals. The project ran for more than 20 years before being placed into hibernation in 2020. The silence had been searched by the combined computing power of millions of people, and it had held. Here is the thing most people do not realise about the scope of what SETI has actually searched. Despite 6 decades of effort, despite the growing sophistication of our instruments and the expanding scale of our programs, we have examined only a tiny fraction of the total search space available to us. Think of it this way. Imagine the full range of possible signals across all frequencies from all directions at all times as an ocean. The volume of that ocean is almost incomprehensibly large. In 6 decades of searching, we have sampled something roughly equivalent to a single glass of water drawn from that ocean. We have not searched the sky. We have not searched the frequencies. We have scratched the surface of an almost infinite search space with the smallest possible scratching tool. The silence we have recorded is real, and it is significant, but it is not yet comprehensive, and that distinction matters enormously for how we interpret what the silence means. The Allen Telescope Array, funded in part by Microsoft co-founder Paul Allen, was designed to dramatically expand the search. Built in the Cascade Mountains of Northern California, it was planned as an array of 350 individual dishes working in concert, capable of searching millions of star systems simultaneously across a wide range of frequencies. Budget shortfalls meant it was built with only 42 dishes initially, though it remains operational and has contributed meaningfully to the search. The square-kilometre array, currently under construction across sites in South Africa and Australia, promises to be the most sensitive radio telescope ever built, capable of detecting a signal equivalent to an airport radar system from dozens of light years away. When it is fully operational, the search will expand by orders of magnitude. We will be able to listen farther, wider, and more precisely than at any previous point in human history. What we will hear, or fail to hear, remains to be seen. But I want to come back to the human dimension of all this because I think it is easy to get lost in the technology and the statistics and forget what it actually means to spend a life listening. There have been researchers who dedicated entire careers to this search, who passed up more lucrative and more conventionally respected scientific paths because they believed, deeply and sincerely, that the question was worth their life's work. Some of them died before the search produced a confirmed result. Some of them spent 40 or 50 years listening to a silence that never broke. And yet, almost without exception, they did not describe their work as futile. They described it as necessary. They said, with a conviction that I find genuinely moving, that the search itself was important regardless of the outcome, that a species capable of asking whether it was alone had an obligation to try to find out. There is something in that attitude that I keep returning to tonight. The silence after 60-plus years of searching is not nothing. It is data. It is a constraint on our models of the universe. It tells us something, even if what it tells us is uncomfortable and incomplete. And it accumulates with every passing year, every new telescope, every expanded search. The silence is not passive. It is a growing weight, pressing down on our most optimistic assumptions, reshaping what we think is possible. 6 decades of nothing is not the same as 1 decade of nothing. It is a silence that has been tested and retested, probed from 1,000 angles, examined with improving tools, and it has not broken, not once, not yet. And in that unbroken quiet, in that accumulated, carefully gathered absence of an answer, the Fermi paradox sharpens from a curious puzzle into something that feels, late at night, like a truth we are not quite ready to face. It was the summer of 1950, and a group of physicists were walking to lunch at the Los Alamos National Laboratory in New Mexico. The men in that group were not ordinary scientists. They were among the most brilliant and consequential minds of the 20th century, people who had spent years working on some of the most complex and dangerous problems in the history of human knowledge. The conversation that afternoon was light, almost playful. They were talking about a recent New Yorker cartoon that had depicted flying saucers, and the discussion drifted the way lunch conversations do, through jokes and speculation about extraterrestrial visitors. And then one of the men at the table, a compact, intense Italian-American physicist named Enrico Fermi, went quiet for a moment. And then he asked, almost as an aside, a question so simple and so devastating that it has never been satisfactorily answered in the 70-plus years since. He looked up from his food and said, "Where is everybody?" Fermi was not asking naively. He was one of the architects of the nuclear age, the man who built the first artificial nuclear reactor, a Nobel Prize winner who was famous within the physics community for the sharpness and economy of his thinking. What made the question so powerful was precisely that it came from a mind accustomed to doing rapid, back-of-the-envelope calculations that turned out to be exactly right. Fermi had looked at the age of the galaxy, and the number of stars and the reasonable likelihood that some fraction of them harboured planets, and the billions of years available for life to develop and spread, and he had reached a conclusion that he stated as a question rather than an answer. The numbers said the galaxy should be full. His experience told him the galaxy appeared empty. The gap between those two things was not a minor inconsistency. It was a chasm. It was a paradox. And it bore his name from that day forward. Let me walk you through the logic of the Fermi paradox as carefully and as plainly as I can, because its full force is sometimes lost when it is summarized too quickly. Our galaxy is approximately 13 billion years old. Earth is approximately 4.5 billion years old, meaning the galaxy was already more than 8 billion years old when our planet formed. In those first 8 billion years, countless other stars were born, matured, and potentially gave rise to planets of their own. If even a small fraction of those planets produced life, and if even a small fraction of that life became intelligent, and if even a small fraction of that intelligence survived long enough to become technologically capable, those civilizations would have had billions of years more than we have had. Billions of years, not thousands, not millions, billions. Now consider what our own civilization has accomplished in just the last 100 years. We went from the first powered airplane flight to landing on the moon in 66 years. We went from room-sized computers to devices that fit in a pocket and contain more processing power than all of NASA used in the 1960s, and we did that in roughly 40 years. We are already designing probes intended to travel to nearby star systems. We are already building space telescopes capable of analysing the atmospheric chemistry of planets orbiting other stars. If our rate of technological progress continued for even 1 million years, let alone 1 billion, we would be unrecognisable to ourselves. We would be capable of things that currently belong entirely to science fiction. Now ask yourself, why has no civilization that had a billion-year head start on us left any trace that we can find? The physicist Michael Hart formalised this version of the paradox in 1975, making the argument even more pointed. He noted that even if a civilization could only travel at a small fraction of the speed of light, it would still be able to colonise the entire Milky Way galaxy within a few million years. Not a billion years, a few million. Given the billions of years available, any civilization that arose early and was capable of interstellar travel should have reached every corner of this galaxy long before Earth even formed. They should have been here. There should be evidence of them everywhere, on our moon, in our asteroid belt, encoded in the geology of our oldest rocks, and there is none. No radio signals, no engineering on a stellar scale, no evidence of a civilization that rearranged a solar system or dimmed a star to harvest its energy. Nothing. Hart called this fact one, as in the single most important observational fact we have about extraterrestrial intelligence. Fact one, they are not here. Scientists and philosophers have proposed dozens of solutions to the Fermi paradox over the decades, and we're going to explore the most serious and unsettling of them as tonight continues. But I want to pause here and make sure you feel the weight of the paradox itself before we start trying to escape it. Because there is a temptation, when confronted with a deeply uncomfortable truth, to leap immediately to the explanation that makes it least uncomfortable, to say, well, maybe they are out there but just have not reached us yet. Or maybe they are communicating on frequencies we have not thought to listen to. Or maybe they are here and we have simply missed the signs. These explanations are possible, some of them are even plausible, but they all share a common feature. They all require us to explain why, despite billions of years of head start and a galaxy full of potential, no civilization has left a single unambiguous mark that we can detect. The bar for the explanation has to be as high as the mystery it is trying to solve. Here is what I find most striking about the Fermi paradox when I sit with it quietly, the way we are sitting with it tonight. It is not really a question about aliens, not at its core. It is a question about the nature of intelligence and civilization in the universe. It is asking whether something like us, something curious and expansionist and restless and creative, is a common feature of reality or an extraordinary aberration. It is asking whether the universe produces minds the way it produces stars and carbon and gravitational waves as a natural consequence of its laws, or whether mind is something else entirely, something that arose here through an improbable sequence of events so specific and so fragile that it has not been repeated anywhere else we can find. Those two possibilities carry very different implications for everything, for what we are, for how we should treat the civilization and the biosphere we have built, for what it means that you're here, tonight, alive and curious and wondering. Fermi finished his lunch. The conversation moved on to other things. The question he had asked hung in the air above that table, unresolved, and it has been hanging in the air above every serious conversation about the universe ever since. Where is everybody? The sky above you right now is full of stars, billions of them, and not one of them, in all the years we have been listening, has answered. That is either a coincidence or a clue, and working out which one it is may be the most important thing our civilization ever does. In 1998, an economist and philosopher named Robin Hanson published a paper with a title that has stayed with me ever since. The paper was called The Great Filter, Are We Almost Past It? It was not a long paper. It was not written in the language of astronomy or biology, but it contained an idea so clean and so terrifying that it has become one of the central frameworks through which serious thinkers now approach the Fermi paradox. Hansen's argument was simple. The universe is old. Life should be everywhere. It is not. Therefore, somewhere between the formation of a star and the emergence of a galaxy-spanning civilization, there is a step, or a series of steps, so extraordinarily difficult to pass through that almost nothing makes it. Something is filtering out the civilizations. Something is keeping the universe quiet. And the most important question we can possibly ask, with implications that dwarf every political or economic problem our species currently faces, is this. Where in that sequence is the filter? Are we on the near side of it? Or have we already passed through? Let me explain what I mean by that distinction, because it is the hinge on which everything turns. Imagine the full sequence of steps required for a civilization like ours to come into existence. You need a star to form in the right region of a galaxy. You need planets to coalesce around it. You need at least one of those planets to sit in the habitable zone. You need the chemistry of life to arise spontaneously from non-living matter. You need that life to develop the ability to reproduce and evolve. You need evolution to eventually produce a multicellular organism. You need that organism to develop nervous systems and then intelligence. You need that intelligence to develop technology, and ultimately the ability to communicate or travel across space. Each one of those steps is a door. Most things that enter the sequence never make it to the end. The Great Filter is the name for whichever door, or doors, are almost impossible to pass through. Now here is where it becomes genuinely frightening. If the Great Filter is behind us, if it is some step early in the sequence that we have already navigated, then there is reason for a strange and cautious hope. Perhaps the origin of life from raw chemistry is extraordinarily difficult, and we were extraordinarily lucky. Perhaps the development of complex multicellular life from simple microbes is a 1 in a trillion accident. Perhaps the emergence of language and abstract thought requires such a specific set of evolutionary pressures that it almost never happens. If any of those early steps is the filter, then we are a miracle. We are the thing that made it through. The silence of the universe exists because almost nothing else did what we did, and we are, in the most literal sense, alone because we are special. But there is another possibility, and this is the one that has kept philosophers and scientists genuinely awake at night for 25 years, since Hansen first wrote his paper. What if the Great Filter is not behind us? What if it is ahead? What if the sequence from single-celled life to technological civilization is actually not that difficult, and civilizations arise relatively frequently across the galaxy, but something reliably destroys them before they can spread? Something that every civilization eventually encounters and almost none survive. A technological threshold that cannot be crossed safely. A self-inflicted catastrophe that intelligent life consistently brings upon itself. A natural event, like a gamma-ray burst or an asteroid impact of civilization-ending scale that periodically resets the clock. If the filter lies ahead of us, then the silence is not evidence of our rarity. It is a warning. It is the quiet left behind by everyone who came before us and did not make it through. Here is the thing most people do not realize about this distinction. It is not merely philosophical, it is empirical. The universe is giving us evidence about which scenario is more likely, and that evidence changes depending on what we find when we look for life elsewhere. Consider this carefully. If we were to discover microbial life on Mars tomorrow, fossilized bacteria in an ancient rock, or active chemistry in the briny water beneath the Martian surface, most people would celebrate that as one of the greatest discoveries in history. And it would be. But it would also be, in a very specific and terrifying way, profoundly bad news. Because if life arose independently on Mars so close to us, in our own solar system, that suggests that the origin of life is not the filter. It is not the hard step. Life gets started relatively easily wherever conditions allow, which means the filter must be somewhere further along the sequence, which means it is probably ahead of us. The same logic applies to the discovery of fossils of complex multicellular organisms or evidence of past intelligence anywhere in the cosmos. Every discovery that suggests life is common pushes the filter further forward in the sequence, closer to where we currently stand. Every confirmation that intelligence arises readily wherever life exists moves the filter to a point we have not yet reached. This is why the astronomer Stephen Webb wrote that a universe teeming with microbial life but empty of intelligent civilizations would be the most terrifying scientific discovery imaginable. It would mean that the almost impossible step is the one between primitive life and the kind of complex technological intelligence that can look up and ask questions, and we are standing on exactly that step right now. What might the filter ahead of us look like? Hansen and those who have built on his work have proposed several candidates. Nuclear war is the obvious one, the self-inflicted catastrophe that a civilization triggers precisely because it develops the technology to destroy itself before it develops the wisdom not to. Climate destabilization is another, the ability to transform a planet's atmosphere faster than any institutional political system can adapt to prevent it. The development of artificial intelligence that surpasses human control before alignment with human values can be ensured. An engineered pathogen released accidentally or deliberately from a sufficiently advanced biotechnology sector. Each of these is a threshold that a civilization must cross, and each carries within it the potential to end what took billions of years to build. The disturbing thing is that we are approaching several of these thresholds simultaneously right now, in the early decades of our own technological maturity. I want to be careful here, because this is not meant to be a sermon or a warning about any specific threat. The Great Filter framework is not a political argument. It is a cosmological one. It is the universe, through its silence, possibly telling us something about the statistical fate of minds like ours. And the fact that we cannot yet hear that message clearly, the fact that we do not know whether the filter is behind us or ahead, is itself one of the most important open questions in all of science. What I can tell you is this: the question of where the filter lies is not abstract. It is not academic. If it is behind us, we are the universe's great miracle, and our survival is its own reward. If it is ahead, then every year we manage to exist and not destroy ourselves and not fall silent is a year the universe has never seen before from a species at our level. Either way, tonight, right now, we are still here, still asking, still listening. That is not nothing. That might be everything. There is a version of the story of life on Earth that we tell ourselves so often we have stopped noticing how strange it is. We say, conditions were right, chemistry did its work, life emerged, and here we are. We say it as though it were a sequence as natural and reliable as water flowing downhill. But in the year 2000, two scientists named Peter Ward and Joe Brownlee sat down and wrote a book that challenged that comfortable narrative at every level. Ward was a paleontologist. Brownlee was an astronomer. Together they argued that the emergence of complex life on Earth was not a natural consequence of reasonable conditions. It was the product of an almost impossibly specific chain of circumstances, each one necessary, each one unlikely, each one stacked on top of the last in a tower of contingency so tall and so narrow that the probability of it standing anywhere else in the universe might be vanishingly small. They called their argument the rare Earth hypothesis. And once you understand it fully, the silence of the cosmos begins to feel less like a mystery and more like an expected outcome. Let us start with the Sun. Our star is, by the standards of the galaxy, quite ordinary. Medium mass, stable output, a lifespan measured in billions of years. But that ordinariness is itself a form of good fortune. The majority of stars in the Milky Way are red dwarfs, smaller and cooler than our Sun, and while red dwarfs have habitable zones, those zones sit very close to the star. Planets in that region are likely to be tidally locked, meaning one face permanently bakes in starlight while the other freezes in eternal darkness. Red dwarfs also tend to be far more prone to violent flares than our Sun, bathing their nearby planets in bursts of radiation powerful enough to strip away atmospheres and sterilize surfaces. The Sun's relative calm and its particular size and temperature have given Earth a stable, temperate environment for billions of years. That stability was not guaranteed. It was not common. It was, in the language of probability, a favourable draw. Now look at where our solar system sits within the galaxy. The Milky Way is not uniform. The central regions are densely packed with stars, which means more gravitational disruptions, more supernovae nearby, more radiation flooding through space. The outer edges of the galaxy are sparse, with fewer heavy elements available to build rocky planets with the chemistry needed for life as we know it. Our solar system sits in a quieter region called the Galactic Habitable Zone, far enough from the danger centre and the sparse outer rim, in a relatively calm stretch of one of the spiral arms. We are, cosmically speaking, in a good neighbourhood, a safe suburb of a galaxy that, in many of its other districts, would be hostile to the kind of long, slow, uninterrupted biological development that produced us. Then there is the Moon. Our Moon is extraordinarily large relative to Earth, far larger in proportion than the moons of any other rocky planet in our solar system. Most planetary scientists now believe the Moon formed when a Mars-sized body collided with the early Earth at a precise angle and velocity, ejecting a ring of debris that eventually coalesced into the satellite we see tonight above us. That collision was catastrophic. It was also, in all likelihood, essential. The Moon's gravitational influence stabilizes Earth's axial tilt, keeping it within a relatively narrow range over millions of years. Without that stabilization, Earth's tilt would wobble chaotically, driven by the gravitational tugs of the other planets, swinging between extremes that would produce climate shifts so violent and so rapid that complex life would struggle to gain any foothold at all. The Moon is not a decoration, it is a gyroscope, and we have it because of a cosmic collision so precisely configured that it seems almost designed, though of course it was not. Then there is Jupiter. The largest planet in our solar system sits in an orbit that has, over billions of years, acted as a gravitational shield for the inner planets. Jupiter's enormous mass intercepts a significant fraction of the comets and asteroids that would otherwise be flung toward Earth by the dynamics of the outer solar system. Without Jupiter, the rate of devastating impacts on Earth would be dramatically higher. Complex life, which requires long periods of stability to evolve, would be interrupted far more frequently by extinction-level events. Mars, which lacks a Jovian shield and sits close to the asteroid belt, shows in its cratered surface what an unprotected inner planet looks like over geological time. We have been luckier than Mars. Jupiter is part of the reason why. The structure of Earth itself adds more layers to this tower of contingency. Our planet has plate tectonics, the slow grinding movement of crustal sections driven by heat from the planet's interior. Plate tectonics is not universal among rocky planets. Mars and Venus, our nearest neighbours, do not have active plate tectonics as we understand it. And yet, plate tectonics may be essential to life over long timescales. It regulates the carbon cycle, drawing carbon dioxide out of the atmosphere through rock weathering and recycling it through volcanic activity, acting as a planetary thermostat that has kept Earth's temperature within a life-sustaining range for billions of years, despite the sun gradually brightening over time. Without that thermostat, Earth would likely have experienced runaway warming or cooling long ago. We would be Venus, or we would be a frozen rock. Plate tectonics kept us neither. And then there is time. Simple microbial life appeared on Earth relatively quickly, within a few 100 million years of the planet's surface cooling. But complex multicellular life took much longer. For approximately 3 billion years, life on Earth remained single-celled. 3 billion years of nothing but microbes, metabolizing, evolving slowly, building up oxygen in the atmosphere through photosynthesis, but producing nothing that you would recognize as complex. The jump from single-celled to multicellular life, which happened roughly 600 million years ago, required a specific set of environmental and genetic conditions that took 3 billion years to assemble. 3 billion years! If Earth had been even slightly smaller, with a faster cooling interior, plate tectonics might have stopped too soon. If the sun had been slightly more variable, sterilizing flares might have reset the clock repeatedly. The window was long, but it was not infinite, and many things had to hold steady for the entire duration. The rare Earth hypothesis does not say life is impossible elsewhere. It says that complex animal-grade life, the kind that builds civilizations and radio telescopes, may require such a specific convergence of stellar, galactic, planetary and geological factors that it is extraordinarily uncommon even in a universe of 2 trillion galaxies. Microbes might be everywhere. Simple chemistry might be churning away on millions of worlds. But the long, unbroken chain of good fortune that led from the first cell to the creature lying here tonight, thinking about all of this, may have been pulled off only once, or only a handful of times, across the entire observable cosmos. If that is true, then the silence is not a paradox at all. It is simply the sound of a universe that almost never manages to produce something complex enough to make noise. And we are the extraordinary exception, existing in a silence that, in the end, might be entirely natural. I want to introduce you to an idea that, once you have heard it, has a way of changing how you look at the night sky. Not gently, not gradually, but all at once, the way a light being switched off changes a room. It is an idea that originated not in a scientific paper, but in a science fiction novel, written by a Chinese author named Liu Cixin and published in 2008 under the title The Dark Forest. But the hypothesis it describes is not fiction. It is a serious proposed solution to the Fermi paradox, and it has been discussed by physicists, philosophers, and astronomers with a seriousness that its origins in literature might not suggest. The dark forest hypothesis does not say the universe is empty. It says the universe is full and that every civilization in it is hiding, deliberately, desperately, because the alternative is death. The logic of the dark forest begins with two axioms, two assumptions about the nature of life in the universe that are, on reflection, very difficult to argue against. The first axiom is that survival is the primary drive of every civilization, just as it is the primary drive of every living thing we have ever observed. Every organism that exists today is descended from an unbroken line of ancestors that survived long enough to reproduce. Survival is not one value among many. It is the foundational value, the one that makes all other values possible. The second axiom is that resources in the universe are finite. Stars burn out. Planets are consumed. The matter and energy available for any civilization to use is limited, and any two civilizations that grow large enough will eventually find themselves in competition for the same finite pool of resources, even if that competition takes millions of years to materialize. From those two axioms, the dark forest hypothesis constructs a chain of reasoning that leads somewhere very cold. If survival is paramount and resources are finite, then any civilization that becomes aware of another civilization faces a fundamental problem of uncertainty. You cannot know, with certainty, whether that other civilization is friendly or hostile. You cannot know their values, their intentions, or how those values and intentions might change over the centuries it would take for any communication or interaction to occur across interstellar distances. And in a universe governed by survival instinct and scarce resources, the safest assumption, the one that maximizes your own chances of survival, is that any civilization you encounter might eventually become a threat. Not necessarily now, perhaps not for 1,000,000 years, but eventually, given enough time and enough expansion, the interests of two civilizations will conflict, and at that point, whichever one struck first will have the advantage. This reasoning leads to what the hypothesis calls the cosmic dark forest state. Every civilization in the galaxy is like a hunter moving through a dark forest. There are other hunters in the forest. You cannot see them clearly. You do not know their intentions, but you know that every other hunter is also reasoning the same way you are, assessing the same risks, weighing the same survival calculus. In that situation, the optimal strategy is silence, absolute silence. You hide your position, you conceal your existence, you do not respond to signals because responding reveals your location. And if you detect another civilization that has revealed its location, you eliminate it before it can grow powerful enough to become a threat. Not out of cruelty, out of pure, cold, rational self-preservation. The dark forest is not a metaphor for evil. It is a metaphor for the inescapable logic of survival in a universe of limited resources and imperfect information. Now here is the part of this hypothesis that I want you to sit with for a moment, because it has a very specific implication for us. Since the early 20th century, our civilization has been broadcasting its existence into space continuously and involuntarily. Every radio transmission, every television signal, every radar pulse sent upward since the 1920s has been radiating outward from Earth at the speed of light. We have been announcing our presence, our location, and something of the nature of our civilization to any sufficiently sensitive receiver within roughly 100 light-years of our planet for over a century. We did not choose to do this as a deliberate act of outreach. It happened as a byproduct of our own internal communication. We lit up, we made noise, and if the dark forest hypothesis is correct, we have been doing the single most dangerous thing a young civilization can do, not knowing the rules of the forest we were born into. Some scientists and thinkers have taken this implication seriously enough to oppose active METI projects, which stands for Messaging Extraterrestrial Intelligence, deliberate attempts to send powerful focused signals toward nearby star systems. Stephen Hawking was perhaps the most prominent voice among those who argued that actively advertising our presence was reckless. He drew an analogy to indigenous peoples who made contact with technologically superior civilizations throughout human history, and noted that those encounters rarely ended well for the less advanced party. The argument is not that extraterrestrial civilizations would necessarily be hostile in any emotional or malicious sense. It is that any civilization capable of reaching us across interstellar distances would be so far beyond us technologically that the interaction, whatever its character, would be one of almost infinite asymmetry. We would not be meeting equals. And yet I want to offer the other side of this, because the dark forest hypothesis, for all its chilling internal logic, rests on assumptions that are not guaranteed to be true. It assumes that the survival instinct and resource competition that govern life on Earth are universal features of all life everywhere. But we genuinely do not know that. It assumes that civilizations remain expansionist and resource-hungry over millions of years, rather than developing past those drives. We do not know that either. It assumes that the communication lag across interstellar distances does not change the strategic calculus in ways we cannot yet model. There are serious scientists who argue that any civilization old enough to become a genuine threat would also be old enough to have moved beyond the paranoid logic of the dark forest entirely, into forms of existence and motivation that we cannot currently imagine. The dark forest hypothesis is not proven. It is a possibility, but it is a possibility that sits in a very specific and uncomfortable place, because if it is true, then our first century of radio broadcasting may have been the worst mistake our species ever made, and we will not know the answer for a very long time. What strikes me most about the dark forest hypothesis is not its terror, though the terror is real and worth feeling. What strikes me is what it says about the nature of intelligence itself. It suggests that minds, wherever they arise, are shaped first, and most deeply by the same forces that shaped the first microbe in the first warm pool of ancient water. Survive, persist, endure. That all the philosophy and art and science and love that intelligence produces may rest on a foundation of fear so old and so deep that it outlasts even the stars. That the silence of the universe may not be emptiness, but caution. Not absence, but concealment. A forest full of eyes, all watching, all waiting, all dark. And we are the ones who started singing. I want you to picture something with me. Picture a stone dropped into a perfectly still pond. The moment it hits the water, rings spread outward from the point of impact, moving in all directions at the same speed, growing wider and wider as they travel, carrying the record of that single disturbance out toward the edges of the pond. Now imagine that the pond is not water, but space, and the stone is not a stone but our entire civilization, every radio broadcast, every television signal, every radar pulse, every deliberate transmission we have ever aimed at the sky. Since the earliest decades of the 20th century, that ring has been spreading outward from Earth in all directions at the speed of light. It is the record of our existence, radiating into the cosmos, and when you calculate how far it has actually travelled, relative to the size of the universe we are trying to speak into, the result is one of the most quietly devastating illustrations of our isolation that I know. Our earliest detectable radio signals date to roughly the 1920s, when powerful commercial and military transmitters first began sending signals strong enough to leak beyond Earth's atmosphere in a form that might, with sufficiently sensitive equipment, be distinguished from natural background noise. That was approximately 100 years ago. Radio waves travel at the speed of light, which means our signal bubble, the spherical region of space into which we have inadvertently announced our existence, is now approximately 100 light-years in radius. 100 light-years sounds large. In the context of daily life, in the context of anything a human mind evolved to comprehend, it is enormous. But our galaxy, the Milky Way, is 100,000 light-years across. Our signal bubble, the entirety of our century-long announcement to the cosmos, covers a sphere that represents 0.1% of the galaxy's diameter. We have whispered into one corner of a single room in an incomprehensibly vast building, and we are wondering why no one in the other rooms has heard us. To make this even more concrete, let me give you a sense of what that 100 light-year bubble actually contains. Within 100 light-years of Earth, there are approximately 3,000 stars. 3,000 out of the 400 billion in our galaxy. If you were to take the Milky Way and reduce it to the size of a continent, our signal bubble would be the size of a dining table sitting somewhere in the middle of it. Every civilization beyond that dining table, assuming any exist, has received exactly nothing from us. Not a single photon carrying the information that Earth exists, that something here is alive, that something here can think and build and broadcast. For the vast majority of our galaxy, we are as silent as the void between stars because our signal has not had time to reach them, and given the distances involved, it will not reach the nearest stars outside our bubble for thousands of years more. And there is a further layer to this that most people have not considered, a layer that makes the bubble even more confining than it first appears. Our signals do not travel through space the way a laser beam travels, focused and intense, aimed at a target. They spread, they diffuse, they thin out as they travel, obeying the inverse square law, which means that every time you double the distance from the source, the signal becomes 4 times weaker. By the time our most powerful early television broadcasts have travelled even a fraction of the way to the nearest star system, Alpha Centauri, roughly 4.2 light-years away, they have weakened to a level indistinguishable from the natural radio noise of the cosmos. We would need extraordinarily sensitive equipment pointed directly at Earth, knowing exactly where to look and what frequencies to scan, to pick up our leakage signals even from our closest stellar neighbour. The idea that alien civilizations are watching our television programs from distant stars, a popular science fiction trope, is almost certainly wrong. Our accidental broadcasts are not broadcasts at all by the time they arrive anywhere interesting. They are whispers that have faded to nothing. This realization prompted a rethinking among some SETI researchers of what kind of signal we should be looking for, and what kind we might ourselves one day choose to send. If leakage radiation is essentially undetectable beyond a few light-years, then the only signals worth searching for are deliberate ones, powerful, focused, narrow-band transmissions aimed specifically at target stars with the intention of being received. This is a very different kind of signal than the ambient radio noise of a civilization going about its business. It requires intent, it requires resources, it requires a decision, made consciously to reveal yourself. And that observation circles back, uncomfortably, to the dark forest. If every advanced civilization understands that leakage is undetectable but deliberate transmission is risky, then every advanced civilization has a strong reason to go quiet, to clean up their radio footprint, to stop leaking. We ourselves, as we move from broadcast television and radio to fibre optic cables and directional digital communications, are already becoming quieter. In another century, Earth may emit almost no detectable radio signal at all, even though our civilization will be more technologically advanced than ever. We will become invisible by accident, simply by improving our technology. There is something almost unbearably poignant about that trajectory when you sit with it. We arrived on the cosmic scene, lit up for a century or two with radio noise, and then, if the pattern holds, we will go quiet again, cloaked by our own technological progress. From the outside, from a distant star, the brief era of our radio visibility would look like a flicker, a flash in the dark that lasted a geological eye blink and then vanished. If another civilization happened to be scanning the right frequency at the right time, aimed in the right direction, they might catch it. The odds of that coincidence occurring are, by any honest calculation, extremely small, and the same logic applies to any civilization we might be trying to hear. Their window of radio visibility may have already closed. They may have gone quiet decades or centuries ago, not because they are gone, but because they got better, because they stopped leaking, because they went dark in exactly the way we are slowly going dark ourselves. So here is where we stand tonight, in the middle of all of this. We exist inside a bubble 100 light-years wide in a galaxy 100,000 light-years across. Our signals are diluted to incoherence within a few light-years. The era during which any civilization leaks detectable radiation may be only a century or two long, a heartbeat in cosmic time. The probability that two civilizations are close enough, and both leaking simultaneously, and both pointed in the right direction at the right moment, is almost vanishingly small, even if the galaxy is teeming with intelligence. The silence we experience may not be the silence of an empty universe. It may be the silence of a universe full of civilizations that have all, one by one, retreated behind the horizon of their own technological evolution, invisible to each other not by choice and not by catastrophe, but simply by the mathematics of distance and time. We're not calling out into nothing. We're calling out into a space so large and our voice is so small that nothing we have said has yet had time to mean anything at all. We have spent most of tonight inside our own galaxy, moving through the Milky Way, examining its stars and its silence, trying to understand why 400 billion suns have produced, as far as we can tell, only one civilization capable of asking about the others. But I want to take you somewhere further now. I want to pull back the camera, slowly, until the Milky Way itself becomes a small thing, a smear of light among other smears of light, and show you the structure of the universe at its largest scales. Because when you see the cosmos from that distance, when you understand what the universe looks like when you zoom out far enough, the loneliness we have been exploring takes on a new dimension entirely. It stops being about planets and signals and radio telescopes. It becomes something structural, something woven into the fabric of the universe itself. Our galaxy belongs to a small cluster of galaxies called the Local Group. The Local Group contains roughly 80 members, most of them small dwarf galaxies orbiting the two largest, the Milky Way and our nearest large neighbour, the Andromeda Galaxy, which sits approximately 2.5 million light-years away. 2.5 million light-years. The light reaching your eyes from Andromeda on a clear night left that galaxy 2.5 million years ago, when our ancestors were still stone tool-using hominids walking the plains of Africa. That is how far away our nearest large galactic neighbour is, and yet by cosmic standards Andromeda is essentially next door. It is so close in relative terms that it and the Milky Way are on a collision course, destined to merge into a single elliptical galaxy in approximately 4.5 billion years. Beyond the Local Group, the universe is organised into structures of increasing scale. Galaxy groups like our own cluster together into larger formations called galaxy clusters, which can contain hundreds or even thousands of galaxies bound together by gravity. These clusters in turn are arranged into superclusters, vast sheets and filaments of matter stretching across hundreds of millions of light-years. Our own supercluster, named Laniakea, a Hawaiian word meaning immeasurable heaven, was only fully mapped in 2014. It spans approximately 500 million light-years and contains the mass of 100 million billion suns. It sounds impossibly large, and it is. But here is what I want you to understand about the structure of Laniakea and structures like it, because this is where the story of cosmic loneliness takes its deepest turn. Between the filaments and sheets of superclusters, there are voids, enormous, almost incomprehensible regions of space that contain virtually nothing. Not a few stars scattered thinly, not a sparse mist of gas and dust. Nothing, or close enough to nothing that the distinction barely matters. The largest known void, called the Bootes Void, is approximately 330 million light-years across. If you were to place our entire Local Group inside the Bootes Void, it would be like dropping a single coin into an empty sports stadium. The coin would not touch the walls, it would not be close to the walls, it would simply float in the middle of a space so vast that even the coin's own shadow would barely reach across it. The Bootes Void is a hole in the universe, a place where the cosmic web has simply left nothing behind. When astronomers first mapped the Bootes Void in 1981, they were so startled by its size that some initially suspected an error in their measurements. Structures that large were not expected to exist within the current age of the universe. The standard models of cosmology at the time suggested that gravity and matter would have distributed themselves more evenly, producing voids, yes, but not voids of that scale. The Bootes Void required a rethinking of how large structures could grow in the time available since the Big Bang. It is now understood as an extreme example of a feature that is actually common in the cosmic web, the tendency of matter to clump along filaments and leave the spaces between those filaments almost entirely empty. The universe, at its largest scales, is mostly nothing. An enormous, intricate web of matter stretched across an ocean of void. Now I want to bring this back to what it means for the question we have been sitting with all night. If civilizations are rare, as the rare Earth hypothesis suggests, then they arise in the densest, most resource-rich regions of the cosmic web, in galaxies clustered along the filaments where star formation has been most active. The voids are not just empty of signals, they are almost certainly empty of the stars and planets that would be prerequisites for any life at all. The loneliness of the cosmos is not uniformly distributed. It has structure, it has geography. There are regions of the universe that are, in a very literal sense, more alone than others, and the voids that separate those regions are so large that no signal, no matter how powerful, sent from one side could reach the other in any time frame meaningful to a civilization measured in millennia rather than billions of years. Think about what it would mean to exist in a galaxy embedded in a void. A civilization on a planet in a galaxy sitting in the middle of the Bhuta's void would look out at their night sky and see something fundamentally different from what we see. They would see their own galaxy, presumably filled with stars, but beyond it, in every direction, for 330 million light years, the sky would be darker than ours. The neighbouring galaxies that we can see from Earth, smudges of light visible to the naked eye in the right conditions, would be absent. The cosmic loneliness we feel here, on this small planet in this ordinary galaxy in a relatively well-populated region of the universe, would be compounded beyond measure for a civilization born into a void. They would have reason to believe, long before they developed radio telescopes, that they were utterly and permanently alone in a way that even we, with all our disturbing silence, have not yet been forced to confront. We are lucky, in a strange and cosmic way, that we live where we do, in a galaxy cluster, in a supercluster, in a region of the universe where other galaxies are visible on a clear night with nothing more than open eyes. The Andromeda Galaxy, 2.5 million light-years away, is visible from Earth without a telescope. We can see it. We know, without instruments, that the universe contains more than us. A civilization born in a void might never have had even that consolation. They might have spent their entire history believing, with complete rational justification, that their galaxy was all there was. Their loneliness would not have been a paradox or a mystery. It would have been their entire observable reality. And yet even here, even with the modest comfort of knowing that other galaxies exist, we have not found a single voice calling back across the dark. The void is not only out there, in those enormous empty spaces between the filaments, it is in the silence. It is in every unanswered signal. It is in the space between what the universe could be, given its size and age, and what it has so far chosen to reveal. In 1998, 2 independent teams of astronomers set out to do something relatively straightforward by the standards of modern cosmology. They wanted to measure how fast the universe was slowing down, not whether it was slowing down, because in 1998 that seemed like a settled question. The universe had been expanding since the Big Bang, and gravity, the mutual attraction of all that matter pulling back on itself across the void, was expected to be putting the brakes on that expansion. The only real question was how much braking was occurring, whether there was enough matter in the universe for gravity to eventually halt the expansion entirely and pull everything back together in what cosmologists called the Big Crunch, or whether the universe would expand forever but at a gradually diminishing rate. Both teams expected to measure deceleration. What they found instead was so unexpected, so fundamentally disorienting, that it rewrote our understanding of the cosmos at the deepest possible level and earned its discoverers the Nobel Prize in Physics in 2011. The universe was not slowing down, it was speeding up. The expansion of space was accelerating. Galaxies were not just moving away from each other, they were moving away from each other faster and faster with every passing moment, driven by something embedded in the fabric of space itself. Something with no agreed-upon physical explanation, something that the scientific community named, with a candour that reveals how little they understood it, dark energy. Dark not because it is sinister, but because it is invisible, undetectable by any instrument we currently possess, identifiable only by its gravitational effect, its push against everything else in the universe. Dark energy appears to constitute approximately 68% of the total energy content of the cosmos. More than 2/3 of everything that exists, in the most fundamental energetic sense, is something we cannot see, cannot measure directly and cannot explain. It is the dominant feature of the universe, and we discovered it less than 30 years ago entirely by accident, while trying to measure something else. Now let me tell you what this means for the long-term geography of our loneliness, because the implications are staggering. Every galaxy beyond our local group, the small cluster of roughly 80 galaxies to which the Milky Way belongs, is currently receding from us. That recession is driven partly by the lingering momentum of the Big Bang and partly by the ongoing push of dark energy. As long as dark energy continues to accelerate the expansion, those galaxies will recede faster and faster. There is a threshold called the Hubble radius, beyond which galaxies are already receding from us faster than the speed of light, not because anything is moving through space faster than light, but because space itself is expanding, stretching the distance between us and them at a rate that light cannot keep pace with. Any light emitted by those galaxies today will never reach us. They are already beyond our permanent horizon. But here is the part that carries the deepest existential weight for our story tonight. The galaxies that are currently just within our observable universe, the ones whose ancient light has had 13.8 billion years to reach us, are not staying within reach. As dark energy continues to push them outward, they will cross the horizon one by one, their light unable to catch up to us any longer, their existence becoming permanently inaccessible. Not in billions of years, in trillions. But the direction is clear and the mathematics is unambiguous. The universe is not a static stage on which civilizations might, given enough time and technology, eventually reach each other. It is a stage that is actively expanding, actively pushing potential partners apart, actively sealing off regions of space from each other with a permanence that no technology we can currently imagine could overcome. In approximately 150 billion years, astronomers have calculated every galaxy outside our local group will have receded beyond our observable horizon. A civilization living at that point in the future, even if it possessed instruments of unimaginable sophistication, would look out at the universe and see only the merged remnant of the Milky Way and Andromeda, surrounded by their small cluster of dwarf galaxies, and beyond that, nothing. Not darkness in the way we experience darkness, as an absence of nearby light sources. Genuine, permanent, structural nothing. The rest of the universe, all 2 trillion minus our handful of local galaxies, will be gone, not destroyed, simply unreachable, invisible, as if they had never existed. Future civilizations, if any survive to that era, will have no way of knowing the universe was ever as large as we know it to be right now. The evidence will have moved beyond the horizon. They will be more cosmically alone than we are, not because the universe will have emptied further, but because its expansion will have hidden its own fullness from them. There is something almost unbearable about that thought, and I want to stay with it for a moment rather than rushing past it. We exist at what cosmologists sometimes call a privileged moment in the history of the universe. Right now, in the 13.8 billion year history of the cosmos, we can still see back to the ancient light of the early universe. We can still detect the cosmic microwave background radiation, the afterglow of the Big Bang itself, a faint whisper of heat left over from the first moments of creation. We can still observe thousands of galaxy clusters and map the cosmic web and understand, at least in outline, the full architecture of what exists. That window is not permanent, it is closing, slowly but irreversibly. The universe is not just expanding, it is becoming less knowable. And that trajectory, from a cosmos that can be observed to a cosmos that is sealed and hidden by its own physics, is perhaps the most profound form of loneliness the universe offers. Dark energy also forces us to revisit, one more time, the silence we have been exploring all night. Even if civilizations exist in other galaxy clusters, even if the universe beyond our local group is teeming with intelligence, those civilizations are already, in a practical sense, permanently beyond our reach. No signal we send will ever arrive. No signal they send will ever reach us. The acceleration of the universe has drawn a circle around our local group that nothing can cross, not because of the speed of a light alone, but because the space between us and them is growing faster than any messenger can travel. We are not just isolated by distance. We are isolated by physics, by the fundamental structure of a universe that chose, for reasons we still do not understand, to push everything apart rather than hold it together. And yet, even knowing all of this, I find something strangely moving in the fact that we figured it out. 2 teams of astronomers, looking at distant exploding stars, measuring the faint light of supernovae billions of light years away, detected the fingerprint of dark energy in the data. They did not go looking for it. They stumbled into it while trying to answer a different question, and they had the honesty and the courage to accept what the data was telling them, even though it contradicted everything they expected to find. We live in a universe that is actively hiding its own nature from us, sealing off its own history, accelerating away from any hope of cosmic community. And we are the things inside it that figured that out anyway. Small, brief, stubbornly curious things, sitting on a pale rock in the dark, working out the shape of a room so large and so strange that it exceeds our ability to truly imagine it. That, at least, is something. On Christmas Day of 2021, a rocket lifted off from a launch pad in French Guiana carrying what many scientists described as the most complex and ambitious scientific instrument ever built by human hands. The James Webb Space Telescope had been in development for over 2 decades. It had cost approximately $10 billion. It had been delayed, redesigned, and nearly cancelled multiple times over its long and troubled journey from concept to launch. And when it finally unfolded in space over the weeks following its launch, deploying its golden mirror and its tennis court-sized sunshield in a sequence of 244 individual mechanical steps, each one of which had to work perfectly or the entire mission would fail, the scientific community held its collective breath. Every single step worked, and what the telescope began to show us in the months and years that followed was so extraordinary that even veteran astronomers struggled to find language adequate to describe it. The first images released to the public in July of 2022 were, by any measure, among the most beautiful and scientifically significant photographs in human history. A cluster of galaxies called SMACS 0723, rendered in such detail and depth that thousands of background galaxies, each one containing hundreds of billions of stars, were visible behind it, their light bent into arcs by the gravity of the foreground cluster. A dying star called the Southern Ring Nebula, its outer shells of gas illuminated in colours and structures never before seen at that resolution. The Carina Nebula, a stellar nursery where new stars are being born, revealed in a panorama of towering gas pillars and infant suns that looked, to every human eye that saw it, like something from the most ambitious science fiction illustration ever created. Except it was real. It was a photograph. It was the universe, showing itself to us more clearly than it ever had before. But for the question that has been at the centre of our journey tonight, the images, as breathtaking as they were, are not the most important thing the James Webb has offered. The most important capability of the telescope, the one that bears most directly on the search for life beyond Earth, is its ability to analyse the atmospheric chemistry of planets orbiting other stars. It does this through a technique called transmission spectroscopy. When a planet passes in front of its host star as seen from Earth, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. Different molecules in that atmosphere absorb different wavelengths of light in characteristic patterns, leaving fingerprints in the spectrum that astronomers can read like a chemical recipe. With previous telescopes, this technique was possible in theory but limited in practice. With James Webb, it became genuinely powerful for the first time. In 2023, the James Webb Telescope examined the atmosphere of a planet called K218b, a world roughly 2.5 times the size of Earth, orbiting a red dwarf star approximately 120 light-years away. What it found in that atmosphere was extraordinary. Carbon dioxide, methane, and tentatively a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, primarily marine phytoplankton. It is what gives the ocean its characteristic smell. Its presence in the atmosphere of a distant world, if confirmed, would be what scientists call a biosignature, a chemical signal that is difficult to produce through purely geological or chemical processes, and that, on our own planet, is made by life. The scientific community responded to this announcement with cautious excitement and significant skepticism in equal measure. The detection was preliminary. The signal was weak. Further observations would be needed to confirm or rule out the finding. But for a brief moment, the silence felt as though it might be cracking. It has not cracked. As of the time I am speaking to you tonight, no confirmed biosignature has been detected in the atmosphere of any exoplanet. The K218b findings remain preliminary and contested. Other candidate planets examined by James Webb have yielded atmospheric data that, while scientifically fascinating, contains no clear evidence of biology. The telescope has found carbon dioxide on multiple worlds, which is interesting for planetary science but not specific to life. It has found water vapour, sulfur dioxide, silicate clouds. It has found that the universe is extraordinarily rich in the chemical precursors to life, and it has found, so far, no life. The most powerful eye we have ever turned on the cosmos is confirming what our less powerful eyes already suspected. The ingredients are everywhere, and the cook appears to be absent. But the James Webb has also done something that I think deserves more attention than it typically receives in popular discussions of the telescope. It has looked backward in time further than any instrument before it, and shown us the early universe in unprecedented detail. Because light takes time to travel, looking at distant objects means looking at them as they were in the past. James Webb can observe galaxies as they existed less than 300 million years after the Big Bang, when the universe was barely 2% of its current age. And what it found there surprised and in some cases troubled cosmologists. Galaxies that were too large, too mature, too well organized to have formed in the time available according to standard models. Ancient galaxies that looked, in some ways, more like modern galaxies than theory predicted they should. The early universe was stranger and more structured than we expected, which means our models of how matter organizes itself over time need refinement. And models that need refinement in one area may need it in others too, including in our estimates of how commonly the conditions for life arise. There is a particular kind of feeling that I think the James Webb Space Telescope produces in anyone who engages with it seriously and honestly. It is a feeling of profound expansion followed immediately by profound humility. The telescope shows you more than you have ever seen, more galaxies, more detail, more chemical complexity, more evidence that the universe is a place of extraordinary richness and variety. And then, in the same breath, it shows you that all of that richness and variety has not yet produced a single, unambiguous sign of another mind looking back. You hold both of those things at the same time, the abundance and the silence, and the tension between them is almost physical. The universe is not withholding. It is showing us everything it has. And everything it has so far does not include a confirmed answer to the only question that, on some level, we have always been asking. Perhaps that answer is coming. The James Webb Telescope has years of operational life remaining, and its schedule of observations is dense with targets that carry the possibility of biosignature detection. Future telescopes, already on drawing boards, will be more sensitive still, capable of examining smaller planets closer to the size of Earth in the habitable zones of sun-like stars. The search is genuinely accelerating for the first time in its history, equipped with tools that are for once almost equal to the scale of the question. What we will find, or fail to find, in the coming decades will do more to answer the question of our cosmic loneliness than everything we have discovered in all the centuries of science before it. The silence may break, but it has not broken yet, and tonight, under the same sky that James Webb is patiently photographing from its orbit 1.5 million kilometers away, the question remains open, enormous, and exquisitely, terrifyingly unanswered. We have been sitting inside difficult ideas all night: the great filter, the dark forest, the accelerating expansion of a universe that is actively sealing itself off from its own contents. Each of these concepts carries its own particular weight, its own flavour of cosmic unease. But I have saved something for this moment, something I have been building toward carefully through everything we have explored together, because I think it requires all of that context to land with its full force. It is not the most frightening possibility in the sense of predicting our destruction. It is unsettling in a quieter, deeper way. It is the possibility that we are not merely rare, not merely isolated by distance and physics and the silence of an indifferent cosmos. It is the possibility that we are first, that in this region of the universe, across a sphere of space containing billions of stars and billions of years of cosmic history, nothing like us has ever existed before. That we are not a late arrival to a party that ended without us. We are the party, we are the first guests, and the hall is empty because no one else has arrived yet. The idea has a name in cosmological circles. It is sometimes called the firstborn hypothesis, and it emerges from a careful look at the timeline of the universe rather than its geography. Most discussions of the Fermi paradox focus on space, on the distances between stars and the impossibility of crossing them. But the firstborn hypothesis focuses on time, on when in the universe's history the conditions for complex life first became possible, and whether we might have arisen at the very beginning of that window rather than somewhere in the middle or the end. If complex life requires certain cosmic conditions, and if those conditions only became available relatively recently in the universe's history, then whoever arose first would find themselves surrounded by silence, not because others failed or hid or were filtered out, but simply because others have not yet had enough time to evolve. Here is the specific argument, laid out plainly. The very early universe, in its first few billion years, was a different place from the cosmos we inhabit now. The first generation of stars, called Population 3 stars by astronomers, were enormous and short-lived, burning through their fuel in millions rather than billions of years. They were also composed almost entirely of hydrogen and helium, the only elements that existed in significant quantities after the Big Bang. They contained no carbon, no oxygen, no nitrogen, no iron, none of the heavier elements that form the building blocks of rocky planets and organic chemistry and life as we understand it. Those heavier elements were forged inside those first massive stars and scattered into space when the stars exploded as supernovae. The universe had to go through at least one full cycle of stellar birth and death before the raw materials for life even existed in meaningful quantities. This stellar recycling took time, significant time. The first rocky planets capable of hosting liquid water and complex chemistry could not have formed until several billion years after the Big Bang, once enough stellar generations had lived and died to seed the interstellar medium with the necessary heavy elements. Earth formed approximately 4.5 billion years ago, when the universe was already 9 billion years old. We are not a young civilization in a young universe. We are a middling-aged civilization in a universe that spent more than half its current life just making the ingredients for us. And here is the critical question that the firstborn hypothesis forces us to confront. How much earlier could the process have started? Was Earth among the first rocky, habitable planets to form? Or are there worlds that had billions of years of the head start on us, sitting around older stars with older chemistry, where life had time to rise and fall and rise again long before our sun ignited? The honest answer, supported by current research, is that Earth appears to be among the earlier generation of potentially habitable rocky planets, but perhaps not by as much as we might assume. Some models suggest that the peak era of planet formation, the period during which the highest number of potentially habitable worlds are being born across the universe, lies not in the past but in the future. In trillions of years, when the current generation of large, bright stars like our Sun have all burned out, the universe will still be full of small, slow-burning red dwarf stars with lifespans of tens or even hundreds of billions of years. Those stars will still be forming planets. Those planets will still have the potential for life. By some estimates, more than 90% of all the potentially habitable planets that will ever exist in the universe have not yet formed. We may have arrived, in the deepest sense, at the very beginning of the universe's long experiment with life. If that is true, then the silence is not a paradox at all. It is simply the silence of a universe that has barely started. We are like the first person to arrive at an enormous venue, standing alone in the entrance hall, hearing nothing but our own footsteps, and mistaking the emptiness of a space not yet filled for the emptiness of a space that never will be. The civilizations that will one day fill the galaxy, if they come at all, may arise millions or billions of years from now, around red dwarf stars still in the early stages of their multi-trillion-year lifespans, on worlds not yet formed from dust clouds still collapsing in the outer arms of galaxies. We cannot hear them because they do not exist yet, and they, when they come, will not be able to find us because we will be long gone, compressed into the geological record of a planet orbiting a star that has by then expanded into a red giant and swallowed everything we ever built. There is a particular kind of loneliness in being first that is different from any other kind. It is not the loneliness of being left behind, or of being too distant, or of having been filtered out by some cosmic mechanism of destruction. It is the loneliness of existing before your time, of arising in a universe that is not yet ready for the kind of company you are looking for, of sending signals into a silence that is silent not because it is hostile or indifferent, but because the ears that might one day hear them are still billions of years from existing. The message in a bottle thrown into the sea will be found, perhaps, but the person who finds it will be born long after the hand that wrote it has turned to dust. I find this possibility, of all the ones we have explored tonight, the most quietly devastating and the most strangely beautiful at the same time. Devastating because it means the cosmic companionship we have been listening for may be a feature of the universe's future, not its present, and we will not live to see it. Beautiful because it means the universe is not finished, because it means life, if it works the way we hope, has barely begun its long story in a cosmos that has trillions of years still ahead of it. We are not the conclusion, we are the prologue. We are the first sentence of a story so long that we cannot imagine its ending. And that sentence, however brief and however isolated it may feel tonight, is one that the universe apparently needed 13.8 billion years to learn how to write. There is a question that I think has been sitting quietly underneath everything else we have explored tonight, patient and persistent, waiting for us to arrive here. It is not a scientific question. It does not have a formula or a dataset or a peer-reviewed answer. It is the question that comes after the science has done everything it can do, and you're still lying here in the dark with the weight of it. The question is simply this: if this is true, if we are alone, or nearly alone, or effectively alone in any way that matters for how we actually live our lives, what do we do with that? How do you take a fact that large and carry it? How do you let it change you without letting it break you? How do you learn to live inside a silence that big without either pretending it does not exist, or being crushed by the understanding that it does? I have thought about this for a long time, and I want to share something with you that I have come to believe, not as a scientific conclusion, but as a kind of hard-won orientation toward the problem. The silence, when you stop trying to make it say something it might not be saying, when you stop waiting for it to resolve into an answer that will release you from the discomfort of not knowing, the silence begins to do something unexpected. It begins to act as a mirror. It reflects back the value of what is here, in this tiny, improbable, inexplicably alive corner of the cosmos, with a clarity that no other perspective can provide. The vastness and the emptiness do not diminish what exists on this planet. They frame it. They give it a context in which its preciousness becomes almost impossible to argue with. Think about what it means, in the light of everything we have explored tonight, that human beings make music, that we tell each other stories in the dark, that we fall in love and grieve and build cities and plant gardens and argue about philosophy and cry at films and feel homesick for places we have never been. In a universe that appears to be almost entirely composed of hydrogen, helium, dark matter, and the cold silence of the void, all of those things are extraordinary beyond any reasonable expectation. The cosmos did not have to produce anything that could want, or fear, or hope, or remember. The laws of physics did not require a creature capable of missing someone, or of feeling the particular ache of a piece of music heard at exactly the wrong moment. And yet here we are, doing all of those things, on a small rock in the silence, and the silence makes every single one of them matter more. There is a philosopher named Albert Camus who wrote, in the middle of the 20th century, about what he called the absurd, the collision between the human need for meaning and the universe's apparent refusal to provide it. Camus was not writing about the Fermi paradox. He did not have a radio telescope. But what he was grappling with was the same fundamental confrontation we have been sitting inside all night. The universe does not answer. It does not confirm. It does not care in any way we can detect, whether we live or die, whether we build or destroy, whether we are kind or cruel to the brief, improbable creatures we find ourselves sharing this planet with. And Camus argued that the only honest response to that realization was not despair, not the comforting fiction of a hidden meaning we have simply not yet found, but something he called revolt. A clear-eyed, defiant, joyful insistence on living and loving and creating in full awareness that none of it is cosmically guaranteed, not in spite of the silence, almost because of it. I think about that framing often when I consider what the cosmic loneliness we have explored tonight actually asks of us, because I think it does ask something, not in the way a teacher asks a student, not with an expectation of a correct answer, but in the way that a very large empty space asks you, by its very nature, to bring something into it. The silence is not an instruction, but it is an invitation to take seriously the extraordinary improbability of everything that is here, to treat the consciousness that arose in this particular corner of the universe after 13.8 billion years of preparation with the gravity it deserves, to recognize that if we are truly alone, or nearly so, then every human voice, every human gesture of care or creativity or curiosity carries a weight that is almost literally cosmic. There is no one else to do what we do. There may never have been. There may not be for a very long time. This is not a comfortable thought, and I do not want to pretend it is. The loneliness of the cosmos, fully understood, does not resolve into easy consolation. But it does, I think, resolve into something. When you know that the nearest star is 4 light-years away, and that beyond the boundary of our local galaxy cluster, the universe is accelerating away from us forever, you look at the person sleeping beside you differently. When you understand that complex feeling, wondering life may have arisen only once in this entire region of space-time, you look at the child playing in the garden differently. When you have sat, even briefly, with the possibility that we are the first sentence in a story billions of years long, you look at the civilization we have built, with all its obvious and catastrophic flaws, and you see something in it that is worth fighting for. Not because it is perfect, because it is the only one there is. The silence also asks us, I believe, to reconsider the scale of our conflicts, the things we are willing to damage and destroy in the pursuit of advantage over one another. When the context is a planet in a solar system, in a galaxy in a void, the borders we draw and the hierarchies we enforce and the things we are willing to let each other suffer for begin to look very different. Not irrelevant, because the suffering is real, and the people experiencing it are real and deserving of care precisely because they are the rare, extraordinary things they are, but absurd in the Camus sense. Absurd in a way that, if we were honest with ourselves in the full light of our cosmic situation, we might find it harder to sustain. The silence, fully heard, is an argument for a different way of being with each other. Not a naive or sentimental argument, a rational one. We are alone in the dark together. That is not nothing. That is, in fact, almost everything. Tonight, as you lie here and let all of this settle, I want to leave you with a single image that I find genuinely comforting, in a quiet and unforced way. Somewhere on the night side of our planet right now, someone is sitting outside under the same sky we've been exploring together. They do not know you. You do not know them. They are separated from you by geography and language and all the ordinary distances of a human life, but they are looking up at the same darkness, at the same stars, feeling perhaps some version of the same smallness and wonder that you are feeling right now. And in that shared moment of looking up, in that simultaneous wordless acknowledgement of the vast silence above, there is a connection as real as any the universe contains. We are alone in the cosmos perhaps, but we are alone together on this particular rock, and for a species that has spent its entire existence in the dark, reaching for something beyond itself, that shared looking up is not nothing. It is the beginning of everything we have ever built that was worth building. We have travelled a long way tonight, from the quiet contradiction at the heart of the Fermi paradox to the deep architecture of a universe built mostly from darkness and silence. We have walked through the Drake equation and felt the weight of its unanswered factors. We have stood beside Jerry Eman as he circled a sequence of numbers and letters on a paper printout and wrote a word that captured in one syllable everything our species has ever felt when it imagined contact across the void. We have sat inside the great filter and tried to locate ourselves within it. We have considered the dark forest and the rare earth and the firstborn hypothesis, each one a different angle on the same essential truth, that we are here, awake and wondering, in a universe that has given us no clear evidence that anything else is doing the same. And now we've arrived at the end of the night, at the place where the journey turns not outward but inward, where the question stops being about what is out there and becomes, finally, about what it means that we are here at all. I want to start this final chapter with something that the astronomer Carl Sagan wrote in 1994, reflecting on a photograph taken 3 years earlier by the Voyager 1 spacecraft. As Voyager prepared to leave the solar system, mission scientists turned its camera back toward the Sun and photographed the planets it was leaving behind. Earth appeared in that image as a point of light less than a pixel wide, suspended in a beam of scattered sunlight against the black of deep space. Sagan called it a pale blue dot, and he wrote that everything our species had ever known, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species, had lived out their lives on that mote of dust suspended in a sunbeam. He was not trying to make us feel small, he was trying to make us feel the full, staggering weight of what that smallness means. Because a thing that small, in a universe that large, that looks up and asks questions, is not diminished by the contrast. it is made extraordinary by it. Here is what I keep coming back to after everything we have explored tonight. The universe is 13.8 billion years old. It contains 2 trillion galaxies. It is 93 billion light-years across in the portion we can observe, and we do not know how much more lies beyond the horizon of what light has had time to reach us. In all of that, across all of that time and all of that space, the only confirmed instance of matter becoming aware of itself, the only known case of the universe producing something capable of contemplating its own existence, is here, on this planet, in the form of living things that evolved from simpler living things over billions of years on a rocky world orbiting an ordinary star in one unremarkable arm of one ordinary galaxy among 2 trillion. That fact is either the most mundane thing imaginable, or it is the most astonishing. I have come to believe, slowly and without any agenda other than honesty, that it is the most astonishing. The physicist Freeman Dyson once wrote that the more he examined the universe and the details of its architecture, the more evidence he found that the universe, in some sense, must have known we were coming. He was not making a religious argument, he was making a mathematical one. The particular values of the fundamental constants of physics, the strength of gravity, the charge of the electron, the mass of the proton, are calibrated with a precision that, if varied even slightly in most directions, would produce a universe incapable of forming stars or atoms or chemistry or life. The universe did not have to be the way it is the way it is, and the way it is a way that produced us. Whether that is coincidence or design or simply the observer effect of living in one of the universes that happen to work, no one can say with certainty. But the specificity of it, the narrowness of the conditions that made tonight possible, is something I find impossible to hold without a sense of something very close to reverence. And then there is this. Even if we are alone, even if the silence is permanent, even if no signal ever comes and no telescope ever resolves the atmospheric fingerprint of another civilization on a distant world, what we are is still something the universe produced. We are not separate from the cosmos, looking at it from outside. We are made of it. The carbon in your body was forged in the core of a star that exploded billions of years ago. The iron in your blood was created in a stellar collision so violent it briefly outshone an entire galaxy. The oxygen you are breathing right now was released by photosynthetic organisms that lived and died in the ancient oceans of this planet before complex animals even existed. You are not a visitor to the universe, you are a part of it, a part that developed the ability to turn around and look at itself. The universe did not simply produce matter. In producing you, it produced a way of knowing itself, and that, regardless of whether it happened anywhere else, is not nothing. It is perhaps the most remarkable thing that has ever occurred. We are the universe noticing itself. We are the cosmos asking what it is. We are 13.8 billion years of stellar evolution and planetary chemistry and biological complexity arriving finally at a creature that can hold all of that in mind and feel something about it. Feel wonder, feel fear, feel the particular ache of a question that has no answer yet. Feel the strange quiet beauty of lying here tonight, under a sky full of stars, knowing what those stars are and how far away they are, and how long their light has been travelling, and what it means that we can know those things at all. That capacity, that awareness, is the most valuable thing the universe has produced that we know of. And if it is rare, if it is precious, if it exists here and perhaps here alone, then the responsibility that comes with it is not a burden. It is an honour almost too large to hold. Thank you for staying with me tonight through all of this, through the paradoxes and the silences and the vast cold scales of a universe that does not whisper back. It means something to me, genuinely, that you are willing to sit inside these questions rather than looking away from them. That willingness, that curiosity, that refusal to let the darkness be simply dark, is the most human thing there is. It is also, as far as we know, the most cosmic thing there is. If this journey resonated with you, if it left you feeling something you want to carry forward, please take a moment to like or share it. It helps these ideas find the other curious minds out there in the dark, the ones who are also lying awake wondering, who also feel the silence and want to understand it rather than fear it. We are a small channel making something we love, and every person who finds it is, in the best possible sense, one more light in a very large room. The next time you step outside at night and look up, I hope you see the sky a little differently than you did before. Not smaller, because you now know what those lights are, but more yours, more ours. You are standing on the only confirmed living world in the observable universe, under a sky that has been sending us light for billions of years without a single confirmed message attached, and you are wondering about it. That wondering is not a small thing. It is the universe doing something it apparently rarely gets to do. Notice itself. Be curious about itself. Reach toward itself across the dark. Sleep well tonight. And keep looking up at the stars. Good night.